Today we discuss about propositional logic. Propositional logic is used for solving complex problems using simple statements called propositions. These propositions can either be true or false, but cannot be both at the same time. Propositions form knowledge representation, reasoning, and decision making in artificial intelligence systems. They also represent facts or conditions about a situation. The propositions are represented using symbols and connected using logical operators. They help in understanding how different facts are related to each other in complex problems. Here we have some examples of propositions. It is Monday. The sun rises from west, which of course is a false proposition. 5 plus 5 equals 15, again another false proposition. And 7 is a prime number, which of course is a true proposition. The propositional logic is also called Boolean logic as it works with the values 0 and 1. In propositional logic, the symbols can be used to represent propositions such as A, B, C, P, Q, R, and so on. Propositional logic consists of an object, relation, or function, and logical connectives. The logical connectives are also known as logical operators. These logical connectives connect two different sentences. The proposition formula, which is always true, is called a valid sentence or tautology. A proposition formula, which is always false, is known as contradiction, while a proposition formula, which has both true and false values, is called a contingency. Statements which are questions, commands, or opinions are not propositions. For instance, where is the student? How are you, John? Or what is your name? These are not propositions. These are questions, commands, other things. Now, the syntax of propositional logic. Propositional logic syntax defines the allowed sentences for knowledge representation. There are two types of propositions. We have atomic propositions and compound propositions. The atomic propositions are the simplest propositions. They consist of a single property symbol and are either true or false. And here we have two examples of atomic propositions. 5 plus 5 equals 10, which is an atomic proposition as it is a true fact, while sun is cold is an atomic proposition as it is a false fact. Compound propositions are constructed by combining atomic propositions using parentheses and logical connectives. And here we have two examples. It is raining today and the street is wet. Which is the logical connective here? It's and, of course, because it connects to different atomic propositions. It is raining today, the first proposition. The second proposition is the street is wet. John is a doctor and he works in Rome. Again, we have two, this is a compound proposition as it is made of two atomic propositions. John is doctor and the second proposition is he works in Rome. And these two propositions are connected by the logical connective AND. Logical connectives are used to connect two propositions or represent a sentence logically. There are 5 main connectives. First one is negation. A sentence, this sign that you see here, it's called negation. Okay, negation P is called negation of P. Conjunction, a sentence. Here we have the sign, the symbol from conjunction. P conjunction Q is called a conjunction. And here we have some examples. John is intelligent and hardworking. This is a combined proposition, okay? Compound proposition, sorry. It's made of two atomic propositions. The first one is John is intelligent, which can be denoted as P. And the second one is John is hardworking, which can be depicted as Q. So we have here P conjunction Q. We have two atomic propositions connected. Next, we have disjunction. Okay, a sentence P. This is the sign for disjunction. This V sign. Okay, P disjunction Q. An example: John is a doctor or engineer. Okay, again we have a compound proposition which is made of two simple two atomic propositions. John is a doctor and John is engineer. And how they can be connected? They can be connected using this disjunction symbol. Okay, P disjunction Q. Okay, so John is the doctor, is denoted as P, and John is the engineer, is denoted as Q. Next, implication. A sentence P implies Q. This is the symbol for implication. Implications are also known as if-then rules. For example, if it is raining, then the street is wet. Okay. Again, this can be broken into two atomic propositions. Proposition P, it is raining, and proposition Q, street is wet. So P implies Q. Next, we have be conditional. Yeah, here it's a minor. It should be 5 instead of 3. A sentence P, this is the symbol for be conditional. P, be conditional 3, is called a be conditional sentence. As an example, if I am breathing, I am alive, can be represented as, again, we can break it into two atomic propositions. P, I am breathing. Q, I am alive. Okay, so P, be conditional Q. Okay, here we have a table, first table with propositional logic connectives. We have yeah, and, or, implies, if and only if, not the technical terms for them, conjunction, disjunction, implication, deconditional, negation. Okay, symbols. Logical operators such as conjunction, disjunction, negation, implication, and deconditional help combine different propositions to represent logical relations. And here we have some examples of propositions. Let's say proposition P, the sky is blue. Okay. This statement can be either be true or false. Next, proposition Q, it is raining right now. Again, this statement can be either be true or false. Or another proposition R, the ground is wet, which of course can be also true or false. Propositions, as we said earlier, can be combined using logical operators to create more complex statements. For instance, P and Q. Okay, going back, the P is the sky is blue. Q is it is raining today. P and Q is the sky is blue and it is raining. Okay, so basically we combine the two propositions. It is true when both P and Q are true. Next, we have P or Q. P disjunction Q. The sky is blue or it is raining. This one it is true if at least one of P or Q it is true. And not P, this one it is not true that the sky is blue. Okay, so basically it's negation of P. It is true if P is false, means the sky is not blue. Now let's discuss about truth tables. In propositional logic, we need to know the truth values of propositions in all possible scenarios. We can combine all the possible combinations with logical connectives and the representation of these combinations in a tabular format, which is called a truth table. The truth tables are used to find the truth value of complex propositions by checking all possible combinations of truth values for their components. They systematically list every possible combination, which helps in making it easy to find how different logical operators affect the overall outcome. Now, let's discuss about the negation operator. If P is a proposition and the negation of P is denoted by negation P, notice the sign, which when translated to simple English means it is not the case that P or simply not P. The truth value of not P or negation P is the opposite of the truth value of P. And the truth table of not P is this one, okay? So this is P when P is true, not P, of course, it's false. While when P is false, not P is true. Example, negation of it is raining today is it is not the case that it's raining today, or simply we can state it as it is not raining today. Oh. Okay, now conjunction. For any two propositions, P and Q, their conjunction is denoted by P and Q, which means P and Q. Okay. The conjunction P and Q is true when both P and Q are true, otherwise they are false. The truth table of P and Q is the following. So here we have the table for the AND operator. We have two propositions, proposition P, proposition Q, and here in the last column we have P conjunction Q, P and Q. So as you probably know, P and Q is true when both the propositions are true. So basically here in the first case, P is true, Q is true, then P and Q is true. In the rest of the cases, the conjunction is false. Example, conjunction of the propositions P, today is Friday, and proposition Q, it is raining today, P and Q is today is Friday and it is raining today. This proposition is true only on rainy Fridays and it is false on any other rainy day or on Fridays when it does not rain. Now let's discuss about the disjunction. For any two propositions P and Q, their disjunction is denoted by P or Q. Okay? P disjunction Q, this sign V, which resembles with V. The disjunction P or Q is true when either P or Q is true, otherwise it is false. The truth values of P or Q is the following. So probably, as you already know, P disjunction Q is true when one of the values is true, one of the propositions is true. So basically, for the first three rows, we have true, while for the last one, when both P and Q are false, P disjunction Q is false. And as an example, the junction of the propositions P, today is Friday, and proposition Q, it is raining today, P or Q is today is Friday or it is raining today. This proposition is true on any day that is a Friday or any day including rainy Fridays, and it is false on any day other than Friday when it also does not rain. Now, SOR, exclusive OR. For any two propositions P and Q, their exclusive OR is denoted by this sign, which means either P or Q but not both. The exclusive OR is true when either P or Q are true, and false when both are true but not both are false. No, sorry, when both are true or both are false. And here we have the table for the exclusive OR operator. So basically, it is true when the propositions have different truth values. So when P is true and Q is false, we have true. When P is false and Q is true, we have true, okay? But when they have the same value, for instance, true, true, or false, false, the result is false. Now, as an example, exclusive OR of the propositions P, today is Friday, and Q, it is raining today, is either today is raining or it is raining today, but not both. This proposition is true on any data that is a Friday or a rainy day, not including rainy Fridays, and it is false on any day other than Friday when it does not rain or rainy Fridays. Now, implication operator. For any two propositions P and Q, the statement if P then Q is called an implication. It is denoted by P implies Q, this arrow to the right. In the implication P implies Q, P is called the hypothesis or antecedent or premise, and Q is called the conclusion or consequence. The implication is P implies Q is also called the conditional statement. The implication is false when P is true and Q is false, otherwise it is true. The truth value of P implies Q is the following. So here we have the table, we have the two columns, P with the propositions P and Q, and here we have P implies Q. So basically, P implies Q is false only when P is true and Q is false. Okay, so starting from something that is true, we cannot arrive to something that is false. In the rest of the scenarios, the result is true. Now, one might wonder that why is P implies Q true when P is false? This is because the implication guarantees that when P and Q are true, then the implication is true. But the implication does not guarantee anything when the premise P is false. There is no way of knowing whether or not the implication is false since P didn't happen. This situation is similar to the innocent until proven guilty stance, which means that the implication P implies Q is considered true until proven false. Since we cannot call the implication P implies Q false when P is false, our only alternative is to call it true. This follows from the explosion principle, which says a false statement implies anything. Conditional statements play a very important role in mathematical reasoning. Thus, a variety of terminology is used to express P implies Q, some of which are listed below. So, if P, then Q, P is sufficient for Q, when P, a necessary condition for P is Q. And now let's an example. If it is Friday, then it is raining today is a proposition which is of the form P implies Q. The above proposition is true if it is not Friday, the premise is false, or if it is Friday and it is raining, and it is false when it is Friday but it is not raining. The condition for double implication. For any two propositions P and Q, the statement P if and only if, okay, notice that is I followed by double F. Q is called a biconditional and it is denoted by this by this sign. The statement P by conditional operator Q is also called a by implication. P by implication Q has the same truth value as P implies Q and Q implies P. The implication is true when P and Q have the same truth values and is false otherwise. The true value for this operator is this one. Okay. So basically the result is true when both propositions have the truth value, the same truth value. So when both are true or both are false. Some other common ways of expressing P by implication Q are P is necessary and sufficient for Q, if P then Q, and conversely P if Q. And as an example, if it is raining today, if and only if it is Friday today. This is a proposition which is of the form P by conditional Q. The above proposition is true if it is not Friday and it is not raining, or if it is Friday and it is not raining. And it is false when it is not Friday or it is not raining. Okay, here we have the truth value with three propositions. So I will skip it. Now, connectives precedence. Propositional connectors or logical operators have a precedence order, similar with the arithmetic operators, that should be followed while evaluating a propositional problem. And here we have the connectives precedence order. The highest precedence has parentheses, then negation, conjunction, disjunction, implication, and the least one is biconditional. For a better understanding, parentheses can be used to make sure of the correct interpretation. And here we have an example. Not R or Q can be interpreted as not R or Q. Logical equivalence is one of the features of propositional logic. Two propositions are logically equivalent if they always have the same truth values in every possible situation. Equivalence shows that different logical expressions can have the same meaning. They can be verified using truth values or by simplifying the statements with logical rules. The statement S implies Q if S then Q is equivalent to not S or Q. This means if S is true, then T must be true is the same as either S is false or T is true. By conditional P Q, P if and only if Q is equivalent to P implies Q and Q implies P. So these are some equivalents that we can use when we want to find the truth value for an expression. In this table, we can see that the columns not A or B and A implies B are identical. Okay, so the third and the fourth and the last column, they have the same values. Here we have true and truth, false and false, truth and truth. So basically the last columns have the same value of truth. So basically they are equivalent, these two expressions. Properties of operators. Logical operators in propositional logic have various important properties that help to simplify and analyze complex statements. We have commutativity. Probably you know from the arithmetic operators, the order of propositions does not matter when using AND or OR. So P and Q is equivalent with Q and P. P or Q is equivalent with Q or P. Associativity. Grouping of propositions does not matter when using multiple ANDs or ORs. Okay, and here we have P and Q and R. Okay, is equivalent with P and parentheses Q and R. Okay, and the same is valid for the OR operator. Distributivity. And or can distribute over each other, which is similar to multiplication and addition in math. Okay, so here we can use distributivity to open the parentheses. Okay, so P and parentheses Q or R is equivalent to P and Q or P and R. Identity. A proposition combined with true or false behaves predictively. So P and true always is the value of P. P or false is always the value of P. Domination. When combined with true or false, some outcomes are always false. Okay, so P or true is always true because at least one of the propositions is true. P and false is false because at least one of the propositions is false. Double negation. Negating a proposition twice cancels out the negation. So negation of P is equal to P. Idempotence. Repeating the same proposition with and or does not change its values. So P and P equals P. P or P equals P. Okay, so it's the same value as P. Here we have De Morgan's law. So when we negate the conjunction of these two propositions, basically the result is equivalent with not P or not Q. The same is here. So basically we change from or to and we negate the two propositions. Absorption. P or and parentheses P and Q is equivalent with P. P and in parentheses P or Q is equivalent with P. Negation. P or not P is true because at least one of the propositions will be true. P and not P is false because at least one will be false. Implication. P implies Q is equivalent with not P or Q. And biconditional Q is equivalent with P implies Q and Q implies P. Some applications of a propositional logic in artificial intelligence. Knowledge representation. Propositional logic is used to represent knowledge in a structured way. It allows artificial intelligence systems to store and manipulate facts about the world. For example, in expert systems, knowledge is encoded as a set of propositions and logical rules. Automatic reasoning. Artificial intelligence uses logical rules such as modus ponens and modus tollens, which help systems to find new conclusions from existing facts and to think logically. For example, here we have modus ponens. If P implies Q and P are true, then Q must be true. And modus tollens is if P implies Q and not Q are true, then not P must be true. Another application is problem solving and planning. It allows artificial intelligence planners to solve problems and to create action sequences by representing goals. Decision making. It helps to evaluate various options and find the best course of action. Logical rules can encode decision criteria, and truth tables can be used to assess the outcomes of different choices. Natural language processing. It is applied in natural language processing, or simply put NLP, for tasks like semantic parsing, where natural language sentences are converted into logical representations. It helps in understanding and reasoning about the meaning of sentences. Now, some limitations of propositional logic. Despite of having many advantages, it has various limitations. Lack of expressiveness. It cannot handle relationships like all humans are mortal. Scalability. The truth values expands exponentially with the number of propositions. So if we have many propositions, the truth table will be very large. Limited inference. It only handles binary truth values, true or false, and cannot represent probabilities, for instance. No quantifiers. Unlike predicate logic, it does not allow the use of quantifiers such as for all, denoted by this sign A inverted, or there exists, denoted by this sign of A to the left. Inability to handle uncertainty. It cannot represent probabilities or partial truths, which helps in making it unsuitable for uncertain situations. And the lack of context awareness. It ignores meaning or context of statements, which limits its ability to interpret nuanced situations. Now let's see some examples of propositional logic. Let's consider the following statements. P. Good mobile phones are not cheap. And the proposition Q. Cheap mobile phones are not good. L. P implies Q. Proposition Q implies P, proposition N, P is equivalent to Q. Which one of the following proposition L, M, and N is correct? A. Only L is true, P implies Q. B. Only M is true, Q implies P. C. Only N is true, P is equivalent to Q. Or D. L, M, and N are true. So let's denote A and B, the two propositions. A. Good mobile phones. B. Cheap mobile phones. P and Q can be written in logic as proposition P. A implies not B, and proposition Q. B implies not A. We can use the truth value, okay? So here we will have the truth values for proposition A. Here we will have the truth values for proposition B. Here for not A, for not B, for A implies not B, and for B implies not A. If we check the values from the two last columns, we can notice that they are equivalent. So basically A implies not B and B implies not A have the same values and they are equivalent. Thus, the statements D, L, M, and N are true. Because P implies Q, Q implies P, and P is equivalent to Q.